Hey everyone, starting section 11.5 today. So in this one, we are going to look at just the first few examples that are in the notes, mainly so that we can just get the basics of writing equations first, and then look at some applications of them later. So um, to start off, we're going to be talking about how we write equations of lines and planes in three-dimensional space, starting off with lines. And going back to what we know about two-dimensional vectors. Remember, when we have a vector that's written in component form, right, we make an assumption that our initial point is at the origin. All right, and as a result, we can think of each component of that vector as being the change in that variable. So in a two-dimensional vector, the x component would be your change in x, and the y component would be your change in y. So if I wanted to find the slope of a line that contains that vector or is parallel to that vector, all I would have to do is change in y over change in x. And if I have a vector in component form, that just means y component divided by x component. Easy peasy. In three dimensions, though, it's not quite that simple, but we do still use direction vectors as a way to basically come up with the slope. So the first big difference between lines in two dimensions and lines in three dimensions is that in three dimensions we use parametric equations, meaning that we have a separate equation for the x coordinate, the y coordinate, and the z coordinate. Okay, and each of these equations requires two things. A coordinate from a point that we know the line passes through, right? And the slope based on the component form of the vector that is parallel to that line or is contained within the line. So if the line passes through x1, y1, z1, and the line is known to be parallel to the vector ABC, then these three equations collectively will describe that one line in three dimensions. Right here, t is what we call a parameter. Um, Essentially, it just means that if I plug in different values, I'll land at different points on the line. One thing I do want to note, though, is that you can express the same line using different sets of parametric equations. The idea would be that if you plug in different values of t, you still end up getting the same points. Right? So with questions like this, there's not just one right answer and everything else is wrong. There's a right answer, but there are other ways that you can express that. In addition to parametric equations, another way that we could represent a line in three dimensions is using what's called symmetric equations. Basically, the idea is that if we were to solve each of these parametric equations for t, then we would get one of the parts of this equation. So like here, if I solve for t, I would have to subtract x1, and then I would have to divide by a. And then for the second equation, same idea. I would have to subtract y1, I would have to divide by b. And for the last one, I'd have to subtract z1 and divide by c. And since all of these expressions are equal to t, then they must be equal to each other. All right, so writing them in this fashion, where they're all equal to each other, is what we refer to as symmetric equations. Right? And just as with parametrics, you can have the same line be described by different symmetric equations, right? Which makes sense because these guys come directly from the parametric equations. So first example, find the parametric and symmetric equations of a line that passes through the point 1, -2, 4, and is parallel to 2, 4, -4. So using what we just talked about, I can write parametric equations for x by taking the coordinate from the point, 1, plus the component from the vector, 2t. For y, same thing. I get the y coordinate from the point, -2, and the slope from the y component of the vector, so plus 4t. And then for z, I take the z coordinate from the point, we get 4, and the slope from the z component of the vector, so minus 4t. And these are the parametric equations. The question also asked us to write symmetric equations. So if I were to solve each of these for t, right, I would subtract 1, divide by 2. So x minus 1 over 2. For y, I would add 2, divide by 4. So y plus 2 over 4. And then for z, subtract 4, divide by -4. So z minus 4 over -4. And these are the symmetric equations. And there we go. Another example. And this kind of goes back to this concept from high school algebra. If I have 2 points, I can always write an equation for a line through those 2 points. That applies for 3 dimensions, except you're writing parametric equations or symmetric equations. So find a set of parametric equations that passes through these 2 points. Okay. So first thing I need to do, I do have 2 possible coordinates I can work with. If I'm writing my parametric equations, that'll give me these different intercepts. But I need this vector to be able to get the slopes. And if I have 2 points, I can actually get the vector v by just arbitrarily, meaning just however I feel, assigning one of them to be initial and the other to be terminal. So if I let -2, 1, 0 be the initial and 1, 3, 5 be the terminal, and I could have done it the other way and I would still end up with the same line, even if the answer doesn't look the same. So x component, we do final minus initial. 1 minus -2, we get 3. 3 minus 1, we get 2. 5 minus 0, we get 5. So the direction vector, v, is 3, 2, 5. So this is either on the line or parallel to the line, just to remind you. Now to write my parametric equations, I can use either of these points to do that. I don't have to use the initial, I don't have to use the terminal, I just need to pick one and go with it. So first off, for x, if I choose the initial term or the initial point to be the point I use, x coordinates -2 plus slope 3t. Y, the y coordinate is 1 plus the slope 2t. And then z coordinate is 0 plus the slope 5t. So this is a set of parametric equations that describes this line. Side note, because you can do this more than one way, you also might get -2 plus t for x, 3 plus 2t for y, and 5 plus 5t for z. And real quick, I want you to think about the relationship here. Let's say I let t be equal to 1 for this set of parametric equations. If t is 1, then x would be equal to -2 plus 3, so x would be 1. If t is 1, then y would be 3. If t is 1, then z would be 5. That basically gave us this point. In a similar way, if I were to plug -1 in for t to these equations, Actually, backtrack. So plugging 1 in for t here gave us this point, meaning it would be identical or equivalent to plugging in 0 for t using the other possible answer. Right? And similar way, if I let t be -1 for this set of equations, I end up getting this point. So t being -1 here would be the same as t being 0 here. So you see, it describes the same line. We get the exact same points from plugging in different values of t, right? So both of these would be correct. And if you had chosen this to be terminal and this to be initial, you would have ended up getting the negative of this vector. So if you got either of these with the signs flipped for the slope, that would also be right. All right, and then I'm going to move on to planes now. So keep in mind that we're not dealing with 2 dimensions. Now we're dealing with 3 dimensions. And in 3 dimensions, you can have points in space, you can have lines in space, you can also have planes in space. It's like if I were to take a sheet of paper and float it in the air somewhere, right? If I were to just snapshot that, that's a plane. And we can write the equation of a plane in a couple of different ways. I forgot something there. Yeah. All right. Basically, you have 2 forms. You have your standard form, you have your general form, and they rely on knowing 2 pieces of information. 2. Yeah. All right. One is any point that's on the plane. All right. So in these 2 forms that are written here, the plane will pass through the point x1, y1, z1. So these numbers come from a point that's on the plane. A, B, and C are actually components of a vector called the normal vector. So normal is another way of saying perpendicular to. So now we have like 3 different words that mean that, right? Perpendicular, orthogonal, when we're talking about vectors, and normal, which you've taken physics, you've learned about normal force, it's the same idea. All right, so perpendicular to the plane. And I want us to use our brains for a sec. I want us to think back to one of the previous videos. What is a thing that I can do to find a vector that is always perpendicular to some other entity? We've already looked at how to do this for a set of vectors. We could use the cross product. Yep. Because remember, all the cross product, the cross product will always produce a vector that is perpendicular to the 2 vectors that you're crossing. Remember, if my 2 vectors are in a piece of paper like this, my cross product is poking directly out. You know what? I can just stop share for a sec. Yeah. So if I have 2 vectors here, normal vector is always perpendicular to both, right? It can be that, it can be that. But the point is, if I take the cross product of 2 vectors, then I will always get something that is perpendicular to both vectors. And here's the thing, in a plane, there we go. In a plane, I can actually find 2 vectors, right? Other important thing to bring up here is that knowing these forms is going to be a very useful tool for us, because in the next video, when we're talking about some of these application problems, we're going to have to be able to look at the equation of a plane and snag information from it. For example, if I'm given the general form, I know that the coefficients a, b, and c give me components of the normal vector. I know that if I'm in standard form, x1, y1, z1 give me a point that's on the plane. So moving on to an example. Find an equation And we want to write our answer in both forms of the, that is not even the right way to spell plane, dude. Yep. Find an equation in both forms of the plane containing these 3 points. All right. And fun fact from geometry, any 3 points will form a plane. Pretty cool. But anyway, so we need to know 2 things. We need to know a point on the plane. We already know 3, so we can pick any of these 3 points to use. But we also need to know the vector that is normal, or a vector that is normal to this plane, right? Meaning that we need to do the cross product of 2 vectors. I can actually make 2 vectors from 3 points. So let's say that we call this one point P, we'll call this one Q, and we'll call this one R. Okay, I can have the vector PQ by assigning one to be the initial, one to be the final. So I'll let P be the initial. Side note, if I assign this to be the initial point, then it also needs to be the initial point on my other vector. But anyway, PQ, we'll do 1 minus 2, negative 1, 4 minus 1, 3, 1 minus 1, 0. The other vector has to have the same initial point. So P has to still be included here. So PR. If I look at PR, negative 2 minus 2, we get negative 4. 0 minus 1, we get negative 1. And 4 minus 1, we get 3. So these are the 2 vectors whose cross product we can take to find the vector normal to the plane. And I say a vector because it doesn't really matter which order you do it in, but you would get different vectors if you did that. It's just one would be the negative of the other, which remember isn't really that big of a deal. So if I were to take the cross product, PQ cross PR, I basically would take the determinant of a 3 by 3 matrix. First row are the unit vectors I, J, and K. Second row are the components of PQ. And the third row are the components of PR. So remember, we essentially are going to decompose this into a bunch of 2 by 2s by eliminating the first row in each of these columns. So if I eliminate first row, first column, the intersection is I. And we're taking the determinant of this 2 by 2, 3, negative 1, 0, 3, minus J. So first row taken out, second column taken out. If I cover that column up, my matrix will be negative 1, negative 4, 0, 3. Plus K. And if I cover up K, we're left with negative 1, negative 4, 3, negative 1. And now if I do my determinants, 9 minus 0 gives me 9i. Negative 3 minus 0, I get negative 3, but because there's already a negative here, it'll be plus 3j. And then positive 1 minus negative 12, which would be positive 13k. So this is our normal vector n. So now that we know the normal vector and we know a point, well, we have our choice of 3 points, we can write our equations in both ways. I'll set off some space here to do that. So first, we'll start with standard form. So we have x component times x minus, and I'm going to pick p, So x minus 2. You could also pick q or r, and you'd still be correct. Plus 3 times y minus 1 plus 13 times z minus 1 equals 0. Oops. Yeah. Equals 0, dude. Okay, it's fine. Put it on that page. Okay, the other way is if I were to just distribute each of these coefficients. So I would get 9x minus 18 plus 3y minus 3 plus 13z minus 13 equal to 0. Right? If I combine like terms, so combine all of these constants together, we get 9x plus 3y plus 13z, then we get minus 34 is equal to 0. So this is my general form. This first one was my standard form. And there we go. Now we know how to write the equation of a line using parametric or symmetric equations. And we know how to write the equation of a plane in both the standard form and the general form.